All right, so here we are to finish up our lecture on Chapter 5, Electronic Structure and Periodic Trends. This is over electron configurations in the periodic table and basically their relationship. And I really like this layout of the periodic table right here because you can actually see the different blocks based on their energy levels. So if we go to energy level 1, we've got a 1s, 2, we've got 2s and 2p, and so on and so on and so on. We even have our f orbitals down here in those series. So we really can quantify that we've got these trends going on based on where they fall in the periodic table. And like we talked about before, Mendeleev, when he was laying out the basic periodic table, knew that there were elements missing, didn't know what they were, but just based off periodic properties, predicted that elements would go in certain spots. And he predicted right. There's been some modifications to Mendeleev's periodic table, but overall he hit it pretty the nail on the head. So different sections or blocks within the periodic table correspond to the S, P, D, and F sublevels like we talked about today. We can build the electron configuration of atoms by reading the periodic table in order of increasing atomic number. So if we look at it, as we increase the atomic number, well, the energy is going to increase as well with that number. So here again is our blocks. We've got our S's all down here, okay? And that would make sense. And you got to think, well, why would that make sense? Well, we talked about it earlier today about the elements that fall into those categories, that they're pretty, active chemically. There's a lot of energy. And they like to combine easily, and that makes sense when we talk about electron configuration and valence electrons. So the S blocks include hydrogen and helium, elements in group 1A and group 2A. Elements in the S block have their final 1 or 2 electrons in the S orbital. All right, we hit that pretty hard today. The P block consists of elements in group 3A through group 8A. There are 6 P block elements in each period because 3 P orbitals can hold up to 6 electrons, right? So we have the S orbitals, they can hold 2 electrons. Now we have the P orbitals, which can hold 6 electrons. All right. We then have the D blocks. Okay. This is contained in our transition elements. The D block sublevels are 1 less than the period number. So if our period number is 4, then the D block sublevel is 3. If the period is 6, the D block sublevel is 5. 6 minus 1. Yeah, there we go, 5. There are 10 elements in each D block. Because of this, 5 D orbitals can hold up to 10 electrons. Remember, we'll have 5 spots. Up arrows first, down arrows to follow. The F block contains inner transition elements, 2 rows at the bottom of the periodic table. Okay, this is where we'd find our friend uranium that we talk so much about. The F sublevel is 2 less than the period number. So whatever the period number is, we just subtract 2, and voila, there's your level. So a 5 would have a periodic level of 7, okay? Or the period number would be 7. So that would give us a 5 as far as the sublevel, okay? There are 14 elements in each block. There are only 7 F orbitals that can hold up to 14 electrons. All right, that makes sense, okay? So we would have 7 blocks. So this is where our SPDF all comes into play when we're talking about our orbitals. Using the periodic table, we can write the electron configuration for silicon. So period 1, 1s block, period 2, the second S block, and 2 P blocks. So that gives us 2s, 2p6, and finally we get into the third period, which is 3s and 3 P blocks. So 3s2, 3p2. So if we wrote it, the entire thing out, it would look like this. So we have our 1s, 2, R2s2, because we've got 2 electrons in each one of those, 2p2 at that level, so we have 6 electrons, our 3s2, which we completely fill, and then our 3p2, which is not completely filled yet because we know that a p suborbital can hold up to 6 electrons. So how do we write electron configurations using sublevel blocks? Well, first we have to locate the element on the periodic table. We need to write the filled sublevels in each order going across each period, and then complete the configuration by counting the electrons in the last occupied sublevel block. So let's look at this. So we're going to locate the element chlorine on the periodic table. Its atomic number is 17, and it's group 7A in period 3. All right, so we go, all right, well, we look at it and it's like 7A, period 3. Okay, we can do this. So we know that it's period 1 is 1s, and that's the hydrogen to helium. Okay, period 2 is lithium to beryllium, and boron to neon. Okay, so that gives us our 2s, 2 and 2p6, and then finally we have our 3s suborbital, which is sodium to magnesium, which is our 3s2. All right, and then our third period we have the 3p, which is aluminum to chlorine, and so we're working our way up to chlorine. So we've got to go through these levels. So we've got our 1s2, our 2s2, our 2p6, okay, our 3s2, and our 3p5. And if we take each one of those numbers, okay, 2 plus 2 plus 6, that gives us 10, plus 2 gives us 12, plus 5 will give us a total of 17. And the atomic number of chlorine, of course, is 17. And, while it's based on the number of protons, as long as we're not talking about an ion, it would be equivalent electrons in the to the protons. So the 4s sublevel fills out before the 3d sublevels because the electrons in the 4s sublevels are slightly lower energy than those in the 3d sublevel. This order occurs again in period 5 when the 5s fills before the 4d sublevel, and in period 6 when the 6x fills before the 5d sublevel. That's why we drop down by 1 sublevel when we get into those transition elements that are dealing with the d suborbitals. So here's some examples from period 4. Okay, so we've got calcium, and then you'll notice that rather than writing all of this, okay, if I cut this off right here, you'll see that it says argon or AR and 4s1. Well, this is our abbreviated, so we take the stable electron configuration of the noble gas preceding the element and then just finish out that last orbital. So if I were, if it were me, I'd much rather write, come down here to zinc, this versus all of this, okay? But we have to understand what the base is for argon before we can truly understand all of this, because we would cut this right here, okay? That's where we would cut it off. So if we look at the 4p blocks, again, gallium, bromine, krypton, we can again see how an abbreviated block would work out much better for us than having to write all those orbitals. And my expectation in class will be when you go to write this that you can easily figure out the abbreviated version. Of course, I'll make you, at least on one, unmercifully, do one total one, but on the other 2 or 3, you're definitely going to do the abbreviated version because it just makes things simpler. And if you can do the abbreviated version, I am assuming that you're understanding how the full setup works. All right, and filling the 3D sublevel, exceptions occur from chromium and copper. In chromium, the 3D sublevel is close to being half filled, which is more stable. Thus, one of the 4s electrons move to the third 3D sublevel. All right, so this is, again, there's always exceptions to the rule. In the case of chromium and copper, this is what happens. So normally, we would have this filled, and then that wiped out. But in the case, since that 3D sublevel is more stable, okay, than the next energy level, all right, we're going to drop back down. We drop back down into there to make it more more stable. Remember I talked about today that all elements, they want to be stable. They're not good with like just being out there and unhappy. You know, they're looking they're looking for a home. Remember, they always want to be like the cool kids. They always want to be stable. They don't want to be reactive. And they're going to do everything in their power to become inert. That's why they combine the way they do. They all want to be like the cool kids. They all want to be like noble gases. So in copper, the 3D sublevel is close to being filled, which is more stable. Thus, again, instead of staying in the 4S, it jumps over here and completes the stability of 3D level in order for, you know, to become more stable, less energy. Okay, so using the periodic table, given the symbols of the elements, which are the following electron configurations. So in this case, you know, we can look at the periodic table, or we can do something funky and just add, right? So we got 2 plus 2 is 4, plus 6 is 10, plus 8 plus 2 plus 6 is 8, so that's 18, and then plus 2 and 9, which is, or 2 and 7, which is 9, giving us the atomic number of 27. So if we go ahead and flip ahead, oh, 27, oh my gosh, that is cobalt. Now, in the case of the elements down here, we would have to know what the argon electric configuration is first. Then we can add the 2 and the 10 and 5 to argon, or if we do the atomic number of argon, we could add it to that, and then that would give us, we'd do the addition of 17 to that, and that goes ahead and gives us bromine. Okay, so pretty straightforward, pretty decent solutions. Again, this is pretty straightforward. Don't let it get you down, and it's not too daunting. You just gotta stay on track and make sure that we're understanding what's going on with the periodic table as far as its properties and the orbitals and suborbitals.